Hello, so welcome here. Now, in the previous one, we have done up to something called the linear transformation and their problems regarding derivatives, and they were like basic derivatives because we proved that the linear transformation is unique, and we also provided some proofs on how to manipulate with limits. So, basically, what we did in the last one is as follows. So I'm just basically writing down what we have done in the last ones so that we understand how to basically come up with the next set of rules and functions for this. So this was the condition for differentiation at the point A. So what we did find was if we are given a function f from the Euclidean space r to the power n to the Euclidean space r to the power m, we have that if it is differentiable at some a belongs to r to the power n, then there exists a linear transformation lambda which is from r to the power n to r to the power m like this, and the following limit satisfies, that is limit h tends to 0, norm of f of a plus h minus f of a minus lambda of h divided by norm of h goes to 0. So this was the whole definition, and we also found out that lambda is unique, right? So this was our findings for the last session. Now in this session we would like to go ahead and prove some more things. So but for that we should take a look at how do actually higher dimensional derivatives work. So if we were to do the following, I'll just write down the question here. Now we are required to find out the derivative at a, that is we have to find out this quantity, that is the derivative of f at a. Now notice that whenever you have like a function from higher dimensions, the derivative is not really a single number as in the case of one variable calculus, right? So it's a derivative from r squared to r, and of course this would mean that it's from r to the power 2 to r to the power 1. So the derivative would be a matrix of dimensions 1 cross 2. So whenever you have a function from r to the power n to r to the power m and you find out its derivative, it's always, the derivative is like always, since it's just a linear transformation, the matrix of the linear transformation would be a m cross n matrix. So here it's 1 cross 2 matrix. Now this means just 1 rows and 2 columns. So anyways, we can get to the part easily. We know that sin x's derivative is just cos x, right? Then now if we were to just guess that the derivative of fxy is just cos of x comma 0, we could have done that, and what we can achieve from that is as follows. We can guess the derivative already. That's one way to solve a problem like this. We can already guess the derivative, and then we can use on that to find out our findings. So we can write like this for two-dimensional functions. So it's just like iterated limits, but this works. Now our linear transformation lambda, we want that to be cosine of a into x, because at a it's basically cosine of a. So we have limit h comma k going to 0. Now after this definition, since we know that so this helps us say that, and since also the numerator consists of only real numbers, we can say that the norm is basically the absolute value, first of all. And when we have this norm thing here, we can understand that since hk is greater than equal to this should be less than equals to limit h tends to 0 sine of a plus h minus sine of h minus cosine of a into h by mod h. But this is already 0. This is 0 because we know that derivative of sine x at a is basically cosine a, right? So we already know this part. And since we know this part, we can conclude this, since this is less than equals to 0, from like our previous experience, we can say that this modulus is also greater than equal to 0, and thus therefore limit is 0. Therefore it is easy to say that d of f, what we want to do is ab, so let us do it from ab. So derivative of f at a comma b is cosine of a. That is our answer. Okay. So this completes our problem. Now it is of paramount importance here that we understand that the rules of one variable calculus sometimes also translate back to this multivariable calculus. That is, we can prove the following. Such that so we are required to prove that if f is a function and f is from r to the power n to r to the power m, and it is differentiable at a belongs to r to the power n, then we are required to prove that it is also continuous at r to the power at a, which is from r to the power n. So this is a direct analog of the property in single variable calculus, which says that if a function f is differentiable at a point a, then it is also continuous at the point a, but it is not necessarily true the other way around, right? Because differentiability is a sufficient condition for continuity, while continuity is just a necessary condition for differentiability. So let us think logically and understand what we can deduce from this. So obviously, let me just write down the given parts first, then we can try and figure out, using all the details we have learned, to see if we can correlate one another. So, well, differentiability at a point in higher dimension means that there exists a linear transformation lambda such that df of a becomes lambda, right? Now, this means that this lambda also satisfies the property that the derivative satisfies. So, we can write down. Now, the limit that norm of f of a plus h minus f of a minus lambda of h divided by the norm of h equals 0 as h tends to 0. This is the limit that it satisfies. So it means that the term in the numerator, which is f of a plus h minus f of a minus lambda h, this term is a good approximation, right, to 0 right now. So there is an error term r of h, if we allow it to happen, that when added to the numerator would give us something like this. So firstly, we understand that f of a plus h is quite well approximated by f of a plus lambda h. But if we want to approximate it further, what we can do is we can write, since there exists an error term which is epsilon of h such that f of a plus h minus f of a is equals to lambda of h plus epsilon of h, where limit h tends to 0, epsilon of h is norm divided by this h is norm goes to 0. And this is true, and you can find out that this is pretty much reasonable, and this also forces the above limit. So this error term must go to 0, right? Now, from this limit it is pretty much clear that since now this is a conclusion that we can make, obviously, and this conclusion gives us a way to frame that the error term goes to 0, the norm of the error term goes to 0, right? Now this says, and also if we can prove that the limit for the linear transformation goes to 0 as h tends to 0, we are done, and you will see why. Because now also if h equals to I equals to 1 to n hi ei. Here ei's are the standard basis of r to the power n, that is here firstly hi belongs to r and ei's belong to r to the power n, where ei is just 0, 0, 1. This is at the ith place, 0 and 0. So this is the standard basis for r to the power n, as we all know from linear algebra. And let us say the vector h is consisting of has this representation, then So that is how lambda of h will be written as. Now, using the properties of linear transformation, we can write this as well. So lambda of this basis, right? Now what we can see is that if h tends to 0, then for all I belongs to 1 comma n, hi tends to 0, right? Because when the vector h goes to 0, all of its components go to 0, and therefore limit h tends to 0, lambda of h is simply limit h tends to 0 and this can be written as and this term goes to 0, right? So we have a 0 in total. So this proves that limit h tends to 0, lambda of h is also 0. And together we have proved something very important. Now what we can do is recall that now taking the limit we have now this proves that since we have this part, obviously, and both of these limits go to 0, so this is 0, and from this we can conclude that therefore limit h tends to 0, f of a plus h is equals to f of a. This means that f is continuous at a. So differentiability implies continuity. So this was not really the hardest problem, because obviously you understand that this problem here uses the basic definitions and just logical thinking to come to the conclusion that differentiability of a function shall always imply continuity. Okay, and that's not really a hard nut to crack. Well, obviously for this to learn this kind of things, you need to be very much wary with all the previous trips of differentiation, derivative using limits from first principles, or the basic definition of limits that we have studied. You need to know those two, and those two will be embedded in this video as well, so you can always find out what to do in those videos. So limits, obviously, as the name suggests, you might have also seen it before, limits are a way to find the limiting value of a function at a certain point. So what I mean by this, when I write lim, it means limit, and under it I have to write the variable and the value it goes to. So this expression right here would mean limit x tends to 2. So theoretically it means this. So in a general way, when x tends to 2, it always means that x not equals to 2. Okay, but it just goes towards 2. So if you can imagine the number line right here and 2 is somewhere around it, let's say this is 1.5 and let's say this is 2.5, then the variable x assumes on these values very close to 2 but never 2 from the left hand side, and it also assumes values from the right hand side very close to 2 but never 2. So the values that this variable assumes goes towards 2 infinitely closer but never actually close enough to be equal, right? In a sense that we can actually evaluate the following thing. So how do we actually evaluate limits? So first we write this, and the question could be something like there could be an expression like this, f of x. Okay, now if this is the limit problem we are trying to evaluate, it will have an answer, limit x tends to 2 f of x. Now the answer could be f of 2. You just put in the value of x here only when f of 2 exists, but in more cases than none, f of 2 will not exist, or putting just the value of the limit will not work. A common example would be like this: limit x tends to 2 this. So as you can see, if we were to put the value here, it will give us 4 minus 4 by 2 minus 2, or 0 by 0, which is practically undefined. It doesn't make any sense at all. Okay, so therefore, like, this kind of problems need to be handled in a bit more subtle way. What we do here is this: we try to eliminate the factor that's making these zeros come, right? We try to eliminate the factor that makes the function undefined. So here this is the factor, and if you can see, the numerator can actually be factorized, right? How? Limit x tends to 2, x plus 2 whole into x minus 2 divided by x minus 2. And now if I were to say that I can cancel the x minus 2's off, it wouldn't be illogical to ask that why can we cancel them off, because they're literally zeros, right? Because x tends to 2, but then x minus 2, if I put the value of 2, it becomes like 0 by 0, and you cannot cancel off zeros. That would be doing literally the same thing, but in fact we can. This is because, as I said you in the earlier part of this video, that whenever I say x tends to 2, this always implies that x is not equal to 2, right? This means that inside the limiting expression, when I'm not putting the value, inside the limiting expression, we can always cancel off the x minus 2's, because x minus 2 is very close to 2 but never 2, so x minus 2 is never 0 actually, because we still have the limit thing on, right? We have not exactly put the value. At the end we put the value of x into the expression, back into the expression, when the function is defined at that point. But before that, whenever we encounter something like the zeros, like this, x minus 2 divided by x minus 2, where both the terms actually evaluate to 0 if we put the value, you can cancel them off, because inside the limit they are not exactly 0, they are close to 0 but not 0. So this gives you limit x tends to 2, x plus 2, right? And now since this is defined at 2, this is not like undefined or infinity or anything like that, we can actually use the value of x to find out this is 2 plus 2, which is 4, which becomes the answer. Okay, so this is a common way to find out limits. And now let us introduce to some of the more basic limits that we shall be encountering. Firstly, a note on this regard: if you have limit x tends to a, where a is a real number, and x to the power n minus a to the power n by x minus a, limits of this form have a general answer, and it is n into a to the power n minus 1. Okay, as you can see in this example, where we had like x tends to 2, x square minus 2 square by x minus 2. Here n was 2 if you can match, and a was 2 as well, so the answer should have been 2 into 2 to the power 2 minus 1, which is 4. So it's a general answer, and why is it true I'm not going to explain right now, because for that we need the factor theorem, or we can use the derivative, which is the L'Hopital's rule, which we shall learn after we learn a bit of derivatives. Before that, it's really hard to evaluate harder limits without using the derivative. So this is the basic which we need to learn here about this formula, and let's do a few examples about this. So example 1 would be limit x tends to 2, x cube minus 2 cube obviously by x minus 2. This is a direct application. And example 2 would be something like this. (27) divided by x square minus 9. Now let us do the problems one by one. Solution to 1. This is a direct application of the formula, so this is just for practice that you remember what we are doing. So x cube minus 2 cube divided by x minus 2. So you can see the n is 3 here and a is 2 here, so it should be n into a to the power n minus 1, right? This just evaluates to 3 into 2 square, which is basically 12, which is the answer. Now this one is a bit easier, but the next part could be a little bit more tricky, because it's not really the formula you think it is, because limit x tends to 3, x cube minus 27 divided by x square minus 9, right? So like before, we can also see that here if we put the value of 3, it becomes like 27 minus 27 divided by 9 minus 9. But we cannot let that happen, because that would just give you a 0 by 0, of course. But we do know that this is in a similar form as to have the formula we just learned, because this can be written as x cube minus 3 cube divided by x square minus 3 square, right? Now one thing you need to know is, whenever limits exist, different portions of the function can be evaluated separately in multiplication and division form, and also in addition form. Okay, so what does this formula is missing? If you look at the formula which I have defined here carefully, you see that we have limit x tends to a, x to the power n minus a to the power n divided by x minus a, right? We are missing that portion. So what portion do we need here? If this limit were to work, we would need a divided by x minus 3, wouldn't we? But how do we get that? Well, luckily there's 2 of those, and obviously you need 2 1 by x minus 3's, right? So if you divide up and down by x minus 3, what you get is this. This is called adjustment. So in more cases, we would actually adjust the limits to a known form like this. We just divided up and down by x minus 3, which is obviously within the rules. And then again you can divide by x minus 3, because x tends to 3 implies x is not equals to 3, right? This is very important, because otherwise there would be no justification of dividing by 0, right, if x were equal to 3. Now these are 2 separate limits, right? And you can see they clearly form in the pattern of the formula we learned, but there are 2 limits and they are in divide form. But as I said, as long as the individual limits would exist, they can be evaluated separately. So basically, since both of these limits exist, it can be written like this. Divided by this. So this would give me like limit x tends to 3, x cube minus 3 cube divided by x minus 3 whole divided by limit x tends to 3, x square minus 3 square divided by x minus 3, right? So this would give me The above portion would be 3 into 3 to the power 3 minus 1, and this one would be n here is 2, so 2 into 3 to the power 2 minus 1, right? So let's evaluate how much that is. This is 3 into 3 square, this is 2 into 3, 3's cancel off, the answer becomes 9 by 2, correct? So this is the answer to our question. So this was a bit tricky, but what I wanted to introduce to you was this concept of adjusting. So we will find limits where we might have to introduce something new in order for it to work, like we just did the 1 by x minus 3 thing here in both the numerator and the denominator. But often, more than not, we might have to introduce some things by known formulas we already know, and we have to make them work like that, right? We have to make them in a form we already know. That's what I'm trying to say. This basically is the first formula that I would like to show you, and let's go on to another one. Another formula is limit x tends to 0 ln of 1 plus x divided by x equals to 1. So this is another formula. Here ln means the natural logarithm, and we are saying that as x tends to 0, the limiting value of logarithm of 1 plus x whole divided by x is equals to 1. Now, how to adjust? That's what I'm trying to make sense here. So let's see. How do we do that? If we had the limit like this, limit x tends to 0 ln of 1 plus 2x whole divided by x, how would we evaluate this? Because this exactly doesn't go with our formula, right? But you need to understand clearly what it means here. It means that when the variable goes to 0, if you have logarithm of 1 plus that variable which goes to 0 divided by the same variable which goes to 0, this particular expression amounts to 1. Okay, so it really means here that limit x tends to 0, if you have a 2 here and you just write it like this, this expression in the limiting value should go to 0 or should go to 1. Why is that? Because see, if x tends to 0, you can treat this as an equation here, so 2x will also go to 0. Okay, this is entirely true because x keeps on decreasing and goes to 0, so obviously 2x will also keep on decreasing and go to 0, maybe at a slower rate, but yes, it will go on, right? So this means that we can write this limit as 2 into limit. Even if you want, you can just substitute for 2x as y and then write y tends to 0, or you can just simply write x tends to 0 or even 2x tends to 0, which you should not write once you get enough practice, but for now it's okay. It will give you 2 into 1, which is 2, right? So I hope the idea is clear that how to actually do these adjustments like we did here and like we are doing here. Let's go to another one. Number 3. We can write another formula here, limit x tends to 0 e to the power x minus 1 by x is equals to 1. Well, this is one of the same things. This is another formula, and obviously if you had something like limit x tends to 0 e to the power 3x minus 1 by 2x, let's say, and if we were to evaluate this, obviously we need to get it to this form. Okay, so the power of e and the denominator must be same, and we have the minus 1 as well, so this should be 1 if given a proper adjustment. So firstly, this 1 by 2 here is the constant. We can take it out and write it as limit x tends to 0 e to the power 3x minus 1 by x, and then we can have a 3 here, so that we do a proper adjustment by making the denominator equal to 3x, and this shall give you 3 by 2 because this portion is just 1, right? Right. So I hope you get the idea. Now it's time to prove two of these things. So proof 1, proof 1, we are trying to prove that limit x tends to 0 ln of 1 plus x by x is equal to 1. Okay, see, this is not a very easy proof, but we can walk our way through it. I'll just show you how. Well, first of all, x tends to 0, so this obviously means that we have that mod x less than 1, since x tends to 0, so x is in the closed neighborhood of 0, right? So it's like an epsilon distance, which is very small. We can consider as small as we want to be, and it's in that distance in between 0. So basically x lies in an interval like this, where minus epsilon to plus epsilon, and epsilon is sufficiently small. Right? So with this expression in mind, what we can do is we are trying to find a series representation for logarithm of 1 plus x, natural logarithm in fact. How do we do that? Not yet, but let us try to use the theory we have used earlier, which is the Taylor series, right? But in this case, we need to find it near 0, so we can use the Maclaurin series directly. We remember that Maclaurin series for fx is given by f of x is equals to summation n equals to 0 to infinity nth derivative of f at the point 0 divided by n factorial into x to the power n, right? And here we have mod x less than 1, since we are trying to find it for logarithm of 1 plus x, which is only defined for minus 1 less than x less than 1. Okay, so the only term we need to find is the nth derivative at the point 0. So let us begin and try to see what happens. So firstly, f of 0 should be ln of 1 plus 0, which is ln of 1, which is 0. So the first term is 0, like the 0th term is 0. Okay, f dashed x in fact would be 1 by 1 plus x, and this would mean f dashed 0 should be 1, right? F double dashed x would be minus 1 by 1 plus x whole squared. So f double dashed 0 should be minus 1. Again, f triple dashed x should be 2 by 1 plus x whole cube, and this would mean that f 30 is 2, right? So this is going to give us a pattern very soon if we just continue it for like 3 to 4 terms, because I do not really want to indulge you with the nth derivative formula directly, which we can calculate directly from here, but let's save that for the derivative portion. So f4 of x again would be minus 6 by 1 plus x whole to the power 4, or in other words, this is just minus 3 factorial by 1 plus x whole to the power 4. So this was give us f40 equals to minus 3 factorial. Let us do 2 more terms. f5x would then be the differentiation of this, which would give you another minus. It will make it a plus, and it will be 4 factorial by 1 by x to the power 5, which would give me f5 of 0 equals to 4 factorial. And similarly, f6 of x should be minus 5 factorial. Judging by it should be minus 5 factorial by 1 plus x whole to the power 6, and this should be equals to minus 5 factorial, right? So as you can see, for the even number of even order of derivative, we have a negative factorial, one less than it, and for the odd we have the positive factorial but one less than the derivative. So we can write that ln of 1 plus x, by the Maclaurin series definition, it should be f0 plus x into f dash 0 plus x square by 2 factorial into f2 0 plus x cube by 3 factorial into f3 0, and so on, right? Now once we start putting in the values, we see that f0 is 0 and f dash 0 is just 1. For the even one it's negative, if you remember, so it's not plus, it's like minus x square by 2 plus x cube by 3 factorial into 2 factorial minus x to the power 4 by 4 factorial into 3 factorial, and so on. Remembering that 3 factorial is just 2 into 3 into 2 factorial, so the 2 factorial will cut off and 3 will remain. Similarly here 3 factorial by 4 factorial will give you a 1 by 4. Continuing in this way, we get the series as x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4 plus x to the power 5 by 5, and so on. So this basically right here is the Taylor series expansion for log of 1 plus x at the point x equals to 0. Now we want to see that in the limiting case, we were trying to prove that limit x tends to 0, ln of 1 plus x by x, right? Now let us write it under, because the series could be a long shot, so we can use the series definition here and we can write it as 1 by x into x minus x square by 2 plus x cube by 3 minus x to the power 4 by 4, and so on. Now since we know that x tends to 0 means x is not equal to 0, we can divide by x and we can find that the answer is 1 minus x by 2 plus x square by 3 minus x cube by 4, and so on, right? Now as I know that we can always put the value of the limit whenever the function is defined, here we just have a bunch of plus and minuses, obviously infinitely many of them, but we can write this as 1 minus limit x tends to 0 and then x by 2 minus x square by 3, and so on, okay? But all of these terms will be 0, because when you put in x equals to 0, it doesn't matter how many of them are infinitely many zeros add up to zeros only, so the answer would be just 1 minus 0, or which is 1, and thus we have proved our limit, right? A similar argument can be made for the next one, where we are trying to prove this, where we are trying to prove limit x tends to 0, e to the power x minus 1 by x equals to 1. So starting with e to the power x equals to 1 plus x square by 2 factorial plus x cube by 3 factorial, and all the way, we can see that if we just take the 1 on the left hand side and divide by x, what we get is this: 1 plus x by 2 factorial plus x square by 3 factorial plus so on. Now if you apply limit to both sides, what you get is this: you get limit x tends to 0 e to the power x minus 1 by x equals to 1, since it's a constant, plus limit x tends to 0 x by 2 factorial plus x square by 3 factorial, and so on. But then again, all of these terms are 0, so the answer should be 1 plus 0, which is 1. right? I have used this definition because I have already showed you how to get the Taylor series for e to the power x in the previous videos. So I just used the result directly. If you really want to revisit, you can just have a look at the previous videos to see how this was derived. I've done it in every step possible. Now this gives the proof for two of our formulas which we learned, and for the first formula as well, we can actually give a outline of the proof of limit x tends to a x to the power n minus a to the power n by x minus a is equals to n into a to the power n minus 1. So this proof is generally given by factor theorem. So let me state the factor theorem here. It's an important result, so if you want you can note it down. The factor theorem says that x to the power n minus a to the power n is equals to x minus a into x to the power n minus 1 into a plus x to the power n minus 2 into a squared, and all the way up to I do not think this was there, yeah, x into a, and at the last term would be a to the power n minus 1. Yeah, this is the factor theorem. So it factors like expressions of the form x to the power n minus a to the power n. So if we were to use this factor theorem, we could easily see that limit x tends to a x to the power n minus a to the power n divided by x minus a would be equal to limit x tends to a x minus a into x to the power n minus 1 plus x to the power n minus 2 into a, and all the way up to a to the power n minus 1 divided by x minus a, right? Now since I have already told you x tends to a means x doesn't equal to a, so we can carefully cross this off, and we are left with limit x tends to a x to the power n minus 1 plus x to the power n minus 2 into a plus x to the power n minus 3 into a squared, and all the way up to a to the power n minus 1. Now putting the value of x, because now this expression is completely defined and it's a polynomial, we see that it is equal to a to the power n minus 1 plus a to the power n minus 2 into a plus a to the power n minus 3 into a squared, and all the way up to a to the power n minus 1. Simplifying, we would get a to the power n minus 1 plus a to the power n minus 1 plus a to the power n minus 1, and all of the terms would be a to the power n minus 1. And how many of them are there? There are n of them, because see, here the power starts from a to the power 0, here the power ends at a to the power n minus 1, so from 0 to n minus 1 inclusive there are n terms, right? So it becomes n into a to the power n minus 1, which is the answer, right? Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.